All right, hi everyone, and welcome back. It's our pleasure to have Ovidiu Savin from Columbia University. He giving his fourth talk, and this is the last talk in the series. And we very appreciate his time and his all the effort to put in the talk. Thank you so much, Ovidiu Savin, please.
Oh, okay, thank you. So yeah, let me just so today I want to talk about an important application to the Monge-Ampère equation, which is the optimal transfer problem. But before I do that, let me just go a bit fast about what we did so far during these lectures. So we are interested in Monge-Ampère equation, which is determinant of d square of u is some right-hand side f. And here we look for convex functions, u, like this. And there are some key properties. So one of them is a fine invariance of the operator, fine invariance. A second important property are interior estimates. Sorry, something happened. Okay. Second property are interior estimates are known as Pogorelov. Interior estimates, which essentially says that if your right-hand side f is very nice, is smooth enough, and is strictly positive, then you can say that, and u is equal to 0 on the boundary of a domain, on the boundary of omega, then we can say that u is in fact very nice inside. Is C, its two derivatives better than f, just like in the cast so let's say u is C3 in omega. Yeah. But this assumption that u is 0 on the boundary of some domain is very important. Yeah, so sort of a consequence of 2 prime is that as long as u is strictly convex and the right-hand side is nice, we have regularity. So let's say if u is strictly convex, then is sufficiently regular. However, the strict convexity is not always guaranteed. So there is, let's say, there is a counterexample of Pogorelov saying that we might have solutions that look like this. Yeah? That even though they are convex, when we look at the tangent plane at a point, we have a whole segment where the function is coincides with the tangent plane. On this line, the function is no longer regular, doesn't have C2 derivatives, so the equation is satisfied in the weak sense. And last time, so let's say in lecture 3 here, what one can really quantify these estimates in the following 3 theorems that I mentioned last time. These are Capharellis Theorems, but they are basically, they stem from whatever I said so far. So it says that if the determinant of this square of u is right-hand side, but the right-hand side is only bounded, doesn't have to be nice enough, I mean, can be discontinuous, if it's bounded between 2 constants, then solutions and sections are compactly included. So in fact, this is the key assumption. So the section, let me remind you that the section, when you give me a convex function u, when you pick a point x0 somewhere on the bottom, you look at the point on the top, on the graph of u, you look at the tangent plane, you go edge up, and then you slice again the graph of u with this tangent plane lifted by edge, and this set, this convex set, is known as the section at height edge at x0. And as long as it is compactly included, you can more or less reduce it to this Pogorelov situation after you subtract the plane that leaves the equation invariant. And this assumption is now that SH of x0 is compactly included in omega. This is always possible if the solution U is strictly convex at x0. Yeah. So if you're in this setting, then if the right-hand side is bounded, then you can actually get interior estimates for the derivatives. So C1 alpha estimates, you cannot expect to have a second derivative estimate simply because f can be discontinuous. However, if f is more regular, if it's Holder continuous, then you can really get this Schauder estimate saying that U is 2 derivatives better. So I would say these are the things, the highlights of what we did so far up to lecture 3. Now in lecture 4, we already start talking about some application to the Minkowski problem and to rigidity of global solution. Now in the last lecture, I would like to insist a little bit more on the optimal transport problem, which is one of the main application of the Monge-Ampère equation. So the optimal transport problem consists in the following. We have a density, a probability density f of x dx, and another one g of y dy, and we're trying to map one into the other by a measure preserving map, but that minimizes a certain cost. So the cost function, denoted here by c of xy, is the cost of transporting from the point x into the point y. Yeah. So if I have to, once I transport some mass from point x into point y, I need to pay a cost. Usually it's supposed to be proportional to the distance. Like a very natural cost would be really to have the distance. Here I'm taking the distance squared just because the algebra works much better, and the Monge-Ampère equation appears very nice when you work with the distance square, but similar properties would be for more general cost functions. I will discuss this at the end. So for the moment, we restrict to the discussion where the cost of transporting x into y is quadratic. And then we say here we want to find the map capital T of x that is measure preserving and that minimizes the total cost. So this T of y here is in fact the image, right? I want to transport x into T of x, which is y squared. And then of course I have to multiply with the mass. If I have more mass at a point, I count it more, according to the measure of the x space. And there is this theorem of Brenier, which says that such a transport map is given in fact by the gradient of a convex function. What I mean by the gradient of a convex function, I really mean the subgradient. So it might be that at some point is multi-valued. So T equals to the gradient of U, or maybe I should say maybe better T belongs to the gradient of U, because at the point, the gradient of U really represents the set of the supporting planes at that point. And how is this related to the Monge-Ampère equation? If you assume that this capital T, the map T, you expected in general to be nice in most of the places. So if you expect this map T to be of class C1, then the fact that T is measure preserving, if you do the change of variable formula, you say g of y dy is the same of g of T of x determinant of d of dt of dx. And this being measure preserving says that this thing has to be f of x. Yeah? So the determinant of dt is determined by the value of f and g at the image point. And on such a region where the map T is of class C1, the function U that is called the potential, right? So the potential satisfies a Monge-Ampère equation of this type. Is the determinant of this square of U equal to a right-hand side, but in the right-hand side we have some terms involving the gradient. Okay, so now I will spend just a bit of time explaining a bit Brenier's theorem, why there is this U convex. How does it appear? Okay, so for that, I want to discuss first a discrete version, and from here one can generalize it by passing to some limits. I'll discuss it later. So a discrete version of this problem simply says that we have n points xi that we want to map them into another point, n points yj, and I want to minimize the sum of xi minus, I want to map each xi into a yj, and I want to minimize the sum of the difference of the distance square. Okay? So in other words, we are trying to minimize among all possible permutations. So we think we try to look at any permutation of the indices I, xi being mapped into some yj. Now, the good thing about the squares is that if we open up the squares, what we end up here, so let me go, right? So if I end up the xi minus y of pi sub I squared, this would be the xi squared minus 2xi dot y pi I plus y pi I squared. And when I sum over all i's, these terms and these terms, they always add up to the same thing, independent of the permutation. So really minimizing the distance square is the same as maximizing the inner product. Yeah. So going back to the slide, either I minimize the distance square or I maximize the sum of the inner product of xi with I have to pair xi with some y, and I do the dot product. If I sum from I equals 1 to n, I want this to be max. So how does this map look like? So you start with just the 2 points being mapped into points. So I have here a picture on the bottom. I have an x1 and an x2 being mapped into other points. And I have 2 choices. Either I map x1 into y1 and x2 into y2, or I map x1 into y1 and x2 into y2. Yeah. So if we label the points so that x1 is mapped into y1, x2 into y2, this is like the maximal, achieve the maximum for this sum. Then we'll have this inequality here that x1 dot y1 plus x2 dot y2 is bigger than or equal than x1 dot y2 plus x2 dot y1, which is equivalent to say that x2 minus x1 dot y2 minus y1 is greater or equal to 0, and this is what is known as monotonicity. Yeah? So whenever you give me 2 points, if I have 2 points here, x1 and x2, and 2 other points, y1 and y2, the way to map them is so that the vector generated by x1, x2, and the vector generated by y1, y2, they have an angle of less than 90 degrees. However, this is not sufficient to really determine, I mean, this is enough to determine the map if I map 2 points to 2 points. But if you have 3 points, let's say if I have 3 points here, so let me erase a bit this picture and say, is monotonicity enough to determine a map? I mean, the minimum, and this is not the case. If you think that you have 3 points, A, B, C, here mapped into 3 red points, I don't know, D, E, F. The question is, which point do I have to map into which point? So if you just try to look for a monotone map, you can always map, I mean, let's say if you map B, so if you map BC, if you map B into D, BC, so let's say if I would map these 3 vectors into these 3 vectors, so that if I map B, let me write here, B into D, and C into E, and A into F, it looks that this map is monotone, but I can also map B into F, and C into D, and A and C into D, and A into E. and this would also be monotone. So in reality, so just by looking at pairs, just per switching pairs 2 by 2 wouldn't determine uniquely the maximal configuration. You really have to try more permutations. And if you try to rotate, so going back to the fact that the sum of xi with y pi is maximal, you also, instead of just having simply monotonicity of the map, you get a relationship like this. That if you take x1, x2, x3 mapped into y1, y2, y3, and you just permute cyclically y1, y2, y3, you still have an inequality. Yeah? Which the inequality in the blue box can be written, let me write it conveniently as in the bottom, that y1 dot x2 minus y, x2 minus x1 plus y2 dot x3 minus x2 plus y3 dot x1 minus x3 is less than or equal to 0. And this, so let's say, so this is known as cyclical monotonicity, which is written here. So if the identity is the maximal permutation for our energy, then if I permute among any cycle, I get, and I look at the product of yi dot x sigma I minus xi, this product is less than or equal to 0. So the way to think about this, let's try to think about that x1 are the points, but let's already think that y1 are some sort of slopes. Yeah. So let's have in mind that x1 is a point, but y1 represents the gradient of some plane passing through x1. So what the cyclical monotonicity says, it says that if I stay at x1 and I travel to x2 using the slope y1, and if I stop at x2 and I travel to x3, but now I'm using the plane of slope y2, and then I travel to x4 using the slope y3 and so on, and you come back to the original point, if you do such a cycle, then the sum of all these heights that you do is going to be less than or equal to 0. You are going to end up below where you started. So that's how it's called cyclical monotonicity. And there is an old theorem of Rockefeller, which says that if a map is cyclically monotone, then it really has to be the gradient of a convex function. So there exists U convex such that yi is a supporting plane of the convex function at xi. Yeah. So, okay, but I mean, this is still not shining light why there is this U. So let's try to understand a bit this equivalence, why cyclical monotonicity and convexity are related. So one implication is very easy. If you look at the convex function and at each xi you pick a slope on the gradient of u that you call yi, then this map would be cyclically monotone. Why? Because by convexity, when I look at the difference at u at x of sigma I minus u of xi, this is greater or equal than the slope of the supporting plane at xi, which is yi. So this is really the gradient of u at xi. Yeah. Dot x pi minus y. This is convexity. Yeah. Now, if I sum all these inequalities, the right-hand side sums to 0. The left-hand side is exactly what I have. So I would get that the map really satisfies cyclical monotonicities in star. Now, why the converse is true? Why, if I have something that is cyclically monotone, there is a convex function u? Yeah. And the way to find this u is constructively, and is more or less like what I said before. So the way you define u at the point xk, so you start at a given point x1, yeah? And you have some sort of ending point xk where you want to define your convex function u. How do you define? So you take all possible paths that go from x1 to xk. So you go through all possible polygonal paths. And then you create the following sum. So from x1, I put the slope y1. I'm thinking that y1 is the slope. I don't know yet. And I'm going to travel from x1 to x2. And then at x2, I'm going to put the slope y2 and travel from x2 to x3. Then I'm going to put the slope y3 and so on. And then I'm going to do this. And at xk, I stop. So sort of, I'm trying to build all this piecewise linear function on these segments and try to find the maximal possible value that I can reach at xk. And I call that the function u. Yeah. So the function u is simply the maximum among all such possible polygonal lines connecting x1 with xk. And then well, cyclical monotonicity tells you, well, if you have, for example, if you have k points, you don't have to worry. But if you have an infinite amount of points, right? Let's say this theorem of Rockefeller is true for any monotone map, not only defined on a finite set. If you have an infinite set, in general, you don't know that u of xk is finite. It might be infinite, but cyclical monotonicity simply tells you that u of xk has to be bounded by some fixed by some fixed quantity, which is the slope, the yk corresponding to xk multiplied with xk minus x0. So this just follows from the definition of cyclical monotonicity. So this function u of xk is well defined in general. For if you just have n points, like or k points, like in our case, we don't have to worry about this inequality. And then by construction, you already satisfy this inequality. Yeah, this inequality. Why you satisfy this inequality? Because if I have a point xl and I take a polygonal path going through xl, and then I travel from xl to xk, the value at xk would be bigger because the xk is the maximal value among all polygonal lines. So if I take a polygonal line that achieves the maximum at xl, and then I do one more step from xl to xk, I will have this inequality, but this inequality simply says that u is convex and yl is a supporting plane for u at xl. So sort of by definition, you get that u is convex. Okay, so this proves Rockefeller theorem, and in some sense it says that it explains why there is this convex function u, and this would be a constructive way of how to build it when you have a finite amount of points. Now there is another shorter proof, but it's not that constructive. So the shorter proof is to say the following. I'm looking for functions u and v that have the following properties. So the functions u would be defined on the points xi. So u is defined on the xi, and v is defined on the target point yj. And I'm looking for pairs uv that have the property that u of xi plus v of yj is always greater than or equal than xi dot yj. So you can always find some u and v like this. You can take u to be constant but very large and v to be constant and very large. So you can always find some functions u and v. But now there is the following claim that the maximal permutation pi that achieves the maximum in the sum of xi with y pi I is exactly the same as the minimum among all pairs of function uv that satisfy this relation, the minimum of the sum. So if I sum over all the points u of xi and v of yj at all this, and I'm trying to minimize among all admissible pairs uv, I get the same answer. So how do you get this claim? So there is a clear inequality. There is an inequality that I always have, that any pair u and v for which u of xi plus v of yj is bigger than xi dot yj would be bigger than any sum xi y pi I. I just have to sum this inequality over the permutation. I just have to take j equals to pi I and sum over I. And so this inequality is always clear. How about the opposite inequality? On the other hand, okay, the opposite inequality holds. So here we see some. So if I take a point xi, so if I take a point xi and I'm looking at u of xi plus v of yj and I range over all j, if I will have strict inequality here for all j, then I wouldn't actually achieve the minimum. I can subtract, I can lower slightly the value of u at xi and not affect anything. Yeah, I mean, the inequalities would still be true. I can replace u just at the point xi with u minus epsilon at that point and lower the minimum of the total sum. Yeah? So what this says, it says that for each I, there exists one j for which I have equality. Yeah? So for every I, there exists a j, and this is the point on which I'm going to map the xi, such that u of xi plus v of yj is equal to x dot yj, and I'm going to call this j pi of I. So this is going to be the permutation that would achieve the maximum value. Okay, and from here, yeah, this is the same u as before. Okay, so anyway, I spent some time explaining Brenier's theorem. Now going back to the original problem, how do we build, I mean, how do we find this transport map from the variable x into the variable y? So now I'm going to the general problem, not discrete, but thinking that I have really a density here, f, that is mapped into a density G. Yeah. Now, so what is difficult is, first of all, it's even if somebody gives you, for example, let's think that f is supported on some set and is identically 1, and G is supported on some other set and identically 1. Yeah. And you try to map one set into the other, they have the same volume, the same area. It's even though the sets are explicit and nice, you can try to think of a square and a ball. It's hard even to write one explicit function that is measure preserving. I mean, it's clear it exists, but if somebody says, just give him one example, because you say you try to minimize among all measure preserving maps, but well, give me one to start minimizing, right? So it's, even this is a bit, we know that it exists, but it's a bit difficult to say it explicit, what it is. I mean, to give one example like this. So then there is this, the way to solve the general problem is first we do some relaxation and say, instead of looking for a map that I map each point x into a point y, what I can try to think that the point x doesn't necessarily have to be mapped into a point y, but I can spread it around. So I can take a point x and think that I chop it, right? It's like I take a column here at the point x, and I'm allowed to transport some piece to a point y and some other piece to a point and to another y and so on. Yeah. This says that actually I'm looking for a transfer plane is called. So I'm allowed to map a point x into several points y. And then if you, the problem, if you express it in this way, it's easier to prove existence. So in this way, in the relaxed version, what we really look for, we look for a probability measure mu defined on the product space on the x and the y, such that when I project mu down, so every time I take a column here and I look at the measure mu restricted to this column, I'm going to get the measure f of x on the bottom, the measure in x. And every time I would take some horizontal strip and I project the measure mu on the y variable, I'm going to get the other measure, the measure g. And this says, this is our condition that the measure is preserving in this transfer plane. And then what we really need to minimize now, we need to minimize the integral of x of the distance square relative to this measure mu, but on the product space, right? This is in sort of Rn cross Rn. So it's the same problem except that in this second one, we are allowed to take a point x and spread it around. And why is more convenient? We are minimizing among all mu's, right? So here, what we are really trying to do, we are trying to find one mu that has this property that the marginals, that their projections are fixed. But among all this probability measure with fixed projection, we are looking for the one that minimizes this cost. And why it's a little bit better, because I can find at least one mu with these marginals, and this would be the product measure. If I take the product measure, sort of if I spread it uniformly x, I spread it everywhere uniformly on the y, each point x, that would be a measure preserving map. It's probably not optimal. It's not optimal to take a column here and spread it equally on the image. But at least I have one example of a measure preserving map. Then just by compactness of measures, you can say that there exists a measure that achieves the minimum. And it's not too difficult then to check that if xy belongs to the support of this measure. So I don't expect this measure really to be spread around, but what I really expect, I expect to be concentrated on some sort of curves like this. This is what I would expect the measure mu to be concentrated. So it turns out that if you take a point, if you take n points on the support of this measure, then just from the minimality, it turns that this map would be cyclically monotone. Yeah. Just because, why is cyclically monotone? It's cyclically monotone because if you give me, let me just explain a bit, well, let me try to move a bit. So you think I have some mass here, the measure mu has some mass here, and has a little bit of a mass here. Yeah? So this would be x1, y1, and this would be x2, y2. Yeah? This is our transfer plane, and here is something on the support of mu. Then what I can do, I can take a little bit of a piece from here and move it onto this square, and a little bit from here and move it into this square, and I don't affect the marginals. Yeah. So I can sort of switch between square 1 and between square 2 and 1. I mean, I have 1, 2, and I can switch sort of into 1 prime and 2 prime, preserving the same marginals. Yeah. And if the sum of x1, so if x1 minus y1 squared plus x2 minus y2 squared is not minimal, if I have better, if I permute x1 and x2, I can lower, I can find the measure still preserving the same marginals, but with lower cost. Yeah. So if you just pay attention to the support of u, it turns out that this is a cyclical, the whole support of mu is cyclically monotone. Oops, sorry. And then it turns out that indeed every y for which, or every xy which is on the support of mu, every y should belong to the subgradient of a convex function, meaning that the support of mu is included on the graph of gradient of u for some u convex. And now at the end you say, well, this is supposed to be single valued almost everywhere. If you give me a convex function it might be multivariate at some point, but almost everywhere is differentiable and the subgradient is uniquely defined. So indeed, we relax the problem, but at the end, we realize that this map is single valued almost everywhere. So this would be Brenner's theorem. Now, okay, so now let's go back to the Monge-Ampère equation. Yeah, I mean not to the Monge-Ampère. Let's go back to the fact that to the case when I have a measure f of x dx g of y dy, and let's assume that they are absolutely continuous with respect to the Lebesgue measure. This means that I have no Dirac deltas in f and g. Yeah? And because the map is single valued almost everywhere, and because on sets of measure 0 I can throw them away because f and g are absolutely continuous with respect to the Lebesgue measure, it turns out that the measure preserving relation really simply says that when I integrate over a set A f of x dx is the same as integrating over the subgrade of the image of the subgradients of A, g of y dy. This is the relationship between measure preserving. Yeah. Now, let's imagine that A and gradient of U of A are bounded sets, and f and g are bounded above and below. Yeah. What this relationship really says here between A and the gradient of U, it says if we are in such a situation that f and g, we can guarantee that f and g are bounded above and below, is that the measure of A and the measure of gradient of U of A are proportional. Yeah? That's what it says, that the area, the Lebesgue measure of A and the measure of the gradient of U of A are proportional if, let me write here, if FG are bounded above and below, on A respectively gradient of U, the image of the gradient of U. So how do I apply? But if A is proportional to the gradient of U of A, this is exactly what an Alexandrov solution says, right? So I'll remind you that when we say that the determinant of d square of U is between capital lambda and small lambda, in reality, what it means in the sense of Alexandrov, what this really means, it means that for any measurable set A, when I look at all the supporting plane of U, to the graph of U on the set A, this is supposed to be less than or equal than capital lambda, the measure of A, and this is bigger than or equal than small lambda, the measure of A, yeah? So the determinant of d square of U being bounded above and below expresses exactly that the image of the supporting plane on a set A is proportional to the measure of the set A, yeah, between two constants. And that's exactly what we would obtain if we can guarantee that f and g are bounded on their supports. So let me do two cases, one simpler, and I mean, there is an issue here if I can really say from star here, I know that star holds, can I guarantee really that A is proportional to the gradient of U at A? So in case one, so this has to do very much with the support of the measures, depends where the measures are supported. So in case one, let's take the case that the support of the measures are, we have them supported on the whole space, F and G. They cannot be bounded, F and G bounded below and above that, but you can think that sort of they decay at infinity. So case one would be, let's assume that F is positive and G is positive and in the whole Rn. Then locally, if you give me if you fix a point X and you look at sets very close to the point X, F there would be bounded on a little region around X, because F would be bounded, it's a nice function, right? Also the gradient image on this little set, because the function U is Lipschitz, would be bounded as well. So in this situation, I could in fact guarantee that locally I would satisfy such a relationship that sets of measure A are mapped by the gradient map into sets of proportional volume. And in that case, I am in the business of saying that actually this U satisfy locally such an inequality. Yeah. But U is a global solution. So last time we said that every time I satisfy such an inequality locally and I deal with global solutions, they have to be strictly convex. And from there locally, you obtain that U is in fact better, is C1 alpha. This is the theorem that we discussed last time. If the determinant is just bounded and strictly convex, then U is in fact C1 alpha. Once U is C1 alpha, I can really say, well, in fact, my equation is really satisfied better. I can talk about really the value of the gradient once you see C1 alpha, and I can write the equation as it is. Then the right-hand side is Holder continuous, and then I can just bootstrap and obtain that U is very nice. Yeah? That U is as nice and as F and G. So I indeed, this optimal transport map is C infinity. So at the end of the day, I obtain that U is C infinity if F and G are C infinity. Yeah? And I will have a single valued map. Yeah. So this will show that the optimal transport map is very nice. Now, case 2 is when the supports of F and G are not spread everywhere. So in the previous case, I used that the supports of F and G are spread everywhere. Let's take the case when the supports of F and G are bounded. Yeah. So the simplest case, we think that F is 1 and G is 1, which means we try to map one set into another set, the two sets, the blue set. So I have here a blue ball mapped into a red patch of the same area, and I'm trying to minimize the quadratic cost function. So one example that people consider to say that in fact the optimal transport map is slightly different than the Monge-Ampère equation. So one such example is when we try to map the unit ball into two half disks that are, I mean, the unit ball, the red unit ball that is broken in the middle and pushed a distance, let's say a distance 2, like this. Yeah. So how would the optimal map look like? So I forgot to say, if you find the function U that already satisfied the equation, I mean, if you already find the convex function U that satisfies the star relation, that it maps one measure into the other by the gradient, then that automatically is the minimum. Yeah? So every time you have uniqueness of this potential U. So here is sort of clear what is the map that you would expect. You would expect that this half ball is translated into the other half ball, and that's exactly what happens. And this other half ball is mapped into the other half ball. And this is in fact the optimal transport map. What is the convex potential? The convex potential is given by 1/2 x squared, the gradient of 1/2 x squared. This is just the identity. Yeah? So if I'm trying to do the identity, the convex potential is 1/2 x squared. But here I'm also trying to push them apart. Yeah. So to push them apart, actually you have to add 2 absolute value of x1. So this is the potential for the transport map in this case. Yeah. However, if you compute the determinant of this square of U as we define it in the sense of measures, yeah. So there are, whenever we define in the first lecture the determinant of the square of U, this is viewed in the sense of Alexandrov. So this is a measure, and the measure to a set A, the measure that the determinant associates is exactly the Lebesgue measure of the supporting gradients. Yeah? If you pay attention here, what happens to the supporting gradients when you sit on this vertical segment, on this diameter, the supporting gradients, in fact, I mean, would just be the whole rectangle in the middle. Let me draw it with orange. Yeah, so I'll say it like this. In reality, what happens with the gradient map is that the half blue disk gets mapped into the half red disk. The left blue half disk goes into the red half disk. But the diameter gets mapped by the gradient map into a whole rectangle, into the whole orange rectangle. However, my measure G doesn't count what is there, while the Monge-Ampère measure does count. The Monge-Ampère measure counts what happens to all supporting hyperplanes. While in our measure preserving map here, what I have on the right-hand side, I integrate over the set of the supporting gradients, but the measure of the target domain. Yeah. So if the measure of the target domain is missing some parts of the space, there might be some mass hidden there. Yeah. So in this case, I cannot go back and say, well, the determinant of this square is bounded between two constants. It's bounded between two constants in this open half disk and in this open half disk, but on the diameter, it has a singularity. It has an edge. And it has a mass, which is recorded here. The mass that it has there is some measure supported on the diameter. So then how can you deal with this case when you have bounded sets? Well, you need to impose a convexity of the target. So Capharellis, he showed that if you deal with bounded supports and let's say F and G are bounded above and below with some constants, and the support of the target is convex. Yeah, if the target is convex, then indeed there is no hidden mass in the Monge-Ampère equation, and you can repeat all the theory and you get that the map is really nice. Yeah. But you need convexity of the target domain. If you don't have that, the map might be discontinuous, as we just saw, right? So in this case, like here, you can try to think of the map in two ways. You can try to think it as the map from the blue set into the red set, and that would be discontinuous. Would be discontinuous about the diameter, but you can also try to think, how about the map from the red set into the blue set? I mean, it's the same thing. I'm just switching the variables. Well, that map would be continuous. My domain is discontinuous, but the map sort of from the red patch into the blue one would be continuous. And this is because the target is convex. Yeah. So if in addition, so you can, in the optimal transfer map, you can reduce everything back in terms of regularity to the Monge-Ampère equation, provided that the supports of F and G are convex. Okay, well, so I took a bit longer than I was expecting. I will just comment maybe 5 minutes about the optimal transportation for more general cost functions. Yeah? So for the quadratic cost function, if you try to minimize the quadratic cost, is the same as maximizing minus x dot y. Yeah, you can try to say, sorry. So if I minimize using the cost C of x y x minus y squared is the same as also saying that I minimize the cost using minus x dot y. The fact that I add a function depending only on x on the cost or a function depending only on y on the cost is irrelevant because they always integrate to the same thing. Yeah? So only sort of the interaction between x and y is important. And we use this to reduce things to convex analysis, yeah, to the fact that the cost function is x dot y. However, everything that I said about the Rockefeller theorem and what we talked can be redone with arbitrary cost functions. And instead of getting that a function is convex, we get that a function is minus C convex. Let me explain what it means minus C convex. So you have a potential U, but now this potential U should tell you how you map the points, how the optimal map maps X into Y. So the way if X gets mapped into Y, the potential U has by below a tangent cost C of XY that is tangent at X. Yeah. So if you think that the cost is X minus Y squared, or let's say X minus Y cubed, this means that the potential U at each point has a translation of X minus Y to the fifth by below. Yeah. And so it would be more or less this. So if somebody gives you some shape here, you say, well, where does this point get mapped? And then you have to look at the slope at that point, and you have to write X, you have to find the orange cost that is tangent at that point, and the vertex of the orange cost, that would be the place where X gets mapped into. It would be so it's exactly the same. What I'm trying to say is exactly the same, but instead of dealing with planes and slope of planes, now we have other functions that are curved planes given by the cost function by below. So whenever I have such a cost by below, you say, well, at the contact point, the gradient of U coincides with the gradient of the cost function. And well, the cost function cannot be arbitrary. The cost function should have some properties, and this relationship should determine Y uniquely. So you need some assumption on the cost function, but the way Y is determined from X is through some sort of nonlinear gradient map relative to the cost C given by this relation. And then when you say, well, what does it mean that is measure preserving? You end up with an equation of this type, yeah, which looks like a deformed Monge-Ampère equation. It's a Monge-Ampère equation that involves this square of U. And the second term, Y here, Y depends on the gradient. Yeah? So as a second derivative of U plus a term involving first derivatives of U that would disappear whenever I have the quadratic term, cost this thing wouldn't be here for the quadratic term. But for general cost function, you have it here. Is not a second order term, is a first order term, so it's a perturbation of the determinant. And then the question is how much of this theory that I talked about, the Monge-Ampère equation, can be done for the cost C of xy? Well, it turns out that if you really look for regularity, you need some strong assumption on the cost function C. And this is known as Mtw condition. This was discovered by Ma, Trudinger, and Wang. And is a condition involving, it's like fourth derivative of C. There is a simpler explanation. So L'Ampère, in fact, characterized geometrically what this Mtw condition is. And this Mtw condition simply says the following, that if I take a cost function, let's say that goes at X and there's vertex at Y, and I take another one that still goes through X and has vertex at Y2, yeah, then sort of all the intermediate ones, like if you want to think all the all the intermediate cost functions should lie below the maximum of the two of them. This is obvious for planes. Sort of, if you give me one plane and if you give me another plane, then they generate an edge, and all the planes in between, they go through that edge and be below the maximum of the two. Sort of the cost functions would need to satisfy a certain property in order to redo the whole theory. And this is known as the Mtw condition. And finally, the Philippis and Figali, I mean, if you don't have this condition, you can still do some partial regularity. Partial regularity meaning that you might not be able to prove that the map is nice at all the points, but almost everywhere with the Lebesgue measure, you can say that is regular. This is a perturbative result in the sense that you expect if you give me a function that is C-convex, you expect by Alexandrov theorem is almost everywhere twice differentiable. And at all these points, when you blow up, you expect to end up really with the function C here should disappear if you do a quadratic blow up at such a point where U is twice differentiable. And essentially that's what the Philippis and Figali did to obtain partial regularity. Okay, I think my time is up, so I'll stop here.
Thank you a lot.